Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the problems on basic computer arithmetic. So, before going to the problems of basic computer arithmetic, we will have a glance on the basics of the computer arithmetic. So, computer is an electronic device. So, computer is an electronic device that can be programmed to accept the data, process it, and generate the results. So, the computer it is made up of some electronic components, and that can be programmed to accept the data. So, the computer can accept the data from the input devices, and after that that input accepted data is processed by the CPU, and then it generates the results, and the generated results will be given to the user for visual purpose. Okay. So the generated results it could be a visual or audio something else. So here, the data is manipulated by using this arithmetic instructions. So, mainly the arithmetic instructions are used to manipulate the data which is present in the registers. Okay. So, the data is manipulated to produce the results necessary to give the solution for computational problems. So, mainly we have four types of arithmetic operations that are addition, subtraction, multiplication, division. So these are the four basic arithmetic operations. So using these four basic arithmetic operations, we can also derive some other operations and to solve the scientific problems by means of numerical analysis methods. So in order to perform these arithmetic operations, we have a separate section called arithmetic and logic unit. So we can also call arithmetic processing unit. So if you look into the architecture of the computer, so mainly it consists of the three parts. So first one is the CPU, memory, and the input output devices. So these are the main three functional parts of the computer. So the CPU is it is a main thing in the computer. So the central processing unit again it is having three parts. First one is the ALU, arithmetic and logic unit, control unit, and some internal registers of the CPU. So this ALU it is responsible to perform various arithmetic operations. So that are addition, subtraction, multiplication, and coming to the logical and or XOR. So there's all these operations are performed by the ALU, and those arithmetic operations we are performing on the data, on the binary data or the decimal data. So the fixed point numbers are used to represent the integers or fractions. So always we are using the fixed point numbers in order to represent the integer or floating fractions. We can have signed or unsigned negative numbers. Fixed point addition is the simplest arithmetic operation. So we can perform the simple operations by using this fixed point numbers. Okay. So if you want to solve any problem, then we use a sequence of well-defined steps. So these well-defined a sequence of well-defined steps is called algorithm. So using this algorithm, we can solve various problems, and we will look into the problems on the uh, arithmetic operations. So first one is perform the arithmetic operations below with binary numbers and with negative numbers in signed 2's complement representation. Use 7 bits to accommodate each number together with its sign. In each case, determine if there is no there is an overflow by checking the carries into and out of the sign bit position. So we are going to perform the arithmetic operations with the binary numbers, with negative numbers in sign to complement representation, and we are using 7 bits in order to represent the number. Okay, so these are the, so we are going to add plus 35 plus 40. So we are going to add the plus 35 and the plus 40, and similarly minus 35 and minus 40. So we are going to add, we are going to perform the addition. And the C bit is the, we are going to perform the subtraction between the minus 35 and the plus 40. So let's see how we can perform these operations. So in order to perform these operations, we should follow some sequence of steps. Okay, so we should follow some sequence of steps so that we can get the result. So first one is convert the decimal numbers into binary. So the given numbers are in the decimal format. So the decimal numbers should be converted into the binary. So that is the first step we have to do. Next one, ensure that both numbers have the same number of bits. So our assumption is we are using a 7 bits in order to represent the number. And third one is perform the arithmetic operation. After that, we are performing that particular operation, whether it is addition or subtraction, multiplication, division, like that. And check for overflow. Finally, we have to check is there any overflow or not. So these are the steps to be followed when you are performing arithmetic operation. So first one is plus 35 plus 40. So we are going to add plus 35 and plus 40. So these two numbers are positive numbers. So we can directly perform the addition operation by converting them into the binary. So first step is convert to binary. So the given number is in the decimal, that we are going to convert into the binary. So how we can convert? So by using this division. So in order to convert to the binary, we have to divide the number with the 2. So here 2 1s are 2 7 14, remainder 1. Next 2 8s are 16, remainder 1. Next 2 4s are 8, remainder 0. 2 2s are 4, remainder 0. Next 2 1s are 2, remainder 0. So after performing this operation, we have to take the sequence in this order. Okay, so that means 1 0 0 1 1. So 1 0 0 1 0 0 1 1. So 1 0 0 1 1. So 6 bits. We got 6 bits, but we are taking 7 bits in order to represent the number. So 7 bits. So that means we are taking 8 bits in order to represent the entire number. So the left side I am taking zeros. Left side I am taking the zeros. I am appending zeros to the left side so that my result will not change. Okay. Similarly, convert the plus 40 into the binary. So if I convert 40 to 20 jar 0, 2 10 jar remainder 0, 2 5 jar remainder 0, 2 2 jar remainder 1, 2 1 jar 2 remainder 0. So this is a sequence 1 0 1 0 0. 1 0 1 0 0. So I got only 6 bits. So remaining 2 bits I am adding to the left side of the number so that my result will not change. So this is a binary conversion. How we can convert the decimal number into the binary. So once we have converted into the binary, then we ensure both have the 7 bits, which they do. Okay. So since we are assuming 7, and the 8th bit is a sign bit. Okay, because the both numbers are positive numbers, so that's why the 0 we are taking. So for positive numbers, so 0 represents positive number, and negative numbers are represented with the 1. Okay, and then we are performing the addition. So if you perform addition, see 1 plus 0 1, 1 plus 0 1, 0 plus 0 0, 0 plus 1 1, 0 plus 0 0, 1 plus 1 1 0. Here 0, here 1 will be there. So 1. Okay. So next, so since if you add plus 35 and plus 40, then you will get result as plus 75. So that's why we are getting the result as a positive number. So that's why the sign of the result is a positive 0. So if you convert into the decimal, so it gives the result as 75, because this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 5, 2 power 6. So 2 power 6 means 64. So we have to convert like 1 into 2 power 6 plus 1 into 2 power 3 plus 1 into 2 power 1 plus 1 into 2 power 0. So we have to add all these so that we will get the decimal value. So 2 power 6, that means 64, plus 2 power 3, 8, plus 2, plus 1. So if you add all these, you will get 75. Okay, so we got the 75. So if you add plus 35 and plus 40, you will get plus 75. So that is the answer. So after that, the fourth step is a check for overflow. Is there any overflow or not? So overflow means if there is any carry out of the MSB. So what is MSB? Out of the sign bit. So this is a sign bit. So if there is any bit in addition to the sign bit, then that will be the overflow. So but here there is no bit out of the sign bit. So that's why here there is no overflow. Here there is no carry out of the sign bit position. So that's why there is no overflow. And next one is a minus 35 plus minus 40. So see here, we are okay. So we are performing the addition between the two negative numbers. Okay. So how we can get the negative number? So the negative numbers always it will be represented in the 2's complemented form. So already we know the plus 35 value. So plus 35. So plus 35 is equal to, see, 1 0 0 1 1. 1 0 0 1 1. So this is a plus 35 equivalent value. Okay, so we are adding zeros here. Okay, so total it will be a 8 bits. So this is plus 35. So how we can write the minus 35? So the negative numbers always we are representing in the 2's complemented form. So 2's complemented form means see here. So in order to get the 2's complemented form value, first we need to perform 1's complement, then we need to add 1 to that 1's complemented value, so that we will get the 2's complemented value. So this is a plus 35. So for that we are performing 1's complement. So 1's complement means complementing. If 0 is there, it will become 1. If 1 is there, it will become 0. So it's a 1's complemented value 1 1 0 1 1 1 0 0. It is a 1's complemented value. I am adding 1 to that. If I add 1, then it will be it is a 2's complemented value. Okay, so this is equivalent to minus 35. Okay, so minus 35 you can see here. You can see 110 110 111 So this is a minus 35. Similarly, minus 40. So already we got the plus 40 value. So then that will be converted into the negative number by performing 2's complementary value. Okay, so second step is ensure both have 7 bits, which they do. Third one, performing the addition. Performing the addition between the minus 35 and the minus 40. So 0 plus 1, 1. 0 plus 0, 0. 1 plus 0, 1. 1 plus 1. If you add 1 plus 1, you will get 0 with the carry 1. So this is a carry. Okay, so if you add 1 plus 1, you will get 0 with the carry 1. Again we are adding 1. So you will get 0 plus 1, 1, 1. So result sum is 1 along with carry also 1. So that's why here 1 and here 1. So you will get 1 again, 1 plus 1. Okay, so 0, 1, 0, 1. And this bit, it is a sign bit, because it is a sign bit. We are using a sign magnitude representation. So MSB, it is a sign bit. So 1, already we have seen, plus 1, 1 it represents a negative number, 0 represents positive number. So it is a MSB bit, sign bit. Okay, so this is equivalent to a minus 75. This is equivalent to minus 75. Suppose if you want this value, so this is the result. So this result is in 2's complementary form. So because we if we add minus 35 and minus 40, the result will be minus 75. So we cannot specify directly the negative values. So the negative values will be represented using the 2's complement form. Okay. So if you want this value, then again it will be converted into the for this data we have to perform the 2's complementary value. So if you perform 2's complementary value, first we need to perform 1's complement. So 0, 0, 1, 0, 0. Okay. So the actual value. So you leave the MSB sign bit, leave the MSB sign bit and take the value. So the value is 1011 0101. For that we are going to perform the 1's complement. So 0 1 0 0 1 0 1 0. So this is a value. So okay, so this is a value we are performing 1's complement. So that 1 0 1 0. Okay, this is 1's complement. If you add 1 to this 1's complement, you will get the 2's complementary value. So if I add 1, the LSB become 1. So this is a result. So what is its equivalent decimal value? 2 power 0, 2 power 1, 2 power 3, 4, 5, 6, 2 power 6. Okay. So already we have seen 2 power 6 means 64, 2 power 3, 8, 2 power 1, 2, 2 power 0, 1, 1. So total 75. Total 75. Okay, so this is plus 75. So this is a negative 75. See, so here MSB is 0 because it is a positive number. But here it is a 1, it is a negative number. So we got the minus 75 as the result. And here, see here, check for overflow. So here in this, there is a overflow because if you see the 7th bit, okay, if you see here, the 7th bit, if you add 1, 1, you will get 1, 0. You will get 1, 0. So, but actually we have to get the 7 bits only. But instead of 7 bits, we got 8th bit. So 8th bit is the overflow. So carry out of the sign bit. So this indicates overflow. Next, minus 35 minus plus 40. So we are performing the subtraction. We are performing the subtraction. So minus 35 minus plus 40. So for subtraction, we can treat its addition with the 2's complement of the second number. Okay. So this we can write minus 35 minus 40. Okay. So minus 35 minus of plus minus 40. So that means we are adding two negative numbers. We are performing addition operation. This is one number, this is another number. We are performing the addition operation between them. Okay, so you will get the result as a minus 75. So same already just before we have seen how we can convert the decimal number into the binary and how we can represent the negative numbers. Okay, so minus 35 you can write. So by taking plus 35, then by performing 2's complement, then you will get the minus 35 value. Similarly, plus 40. Plus 40. So plus 40 in binary. See, plus 40. So plus 40 binary value is this one. Okay. So we want minus 40 value. So by performing 2's complement value, we will get the 2's complement of the plus 40. So if you perform 2's complement on this data, you will get the minus 40 value. Okay, so this is a minus 40 value, and this is a minus 35. So between them, I am performing the addition. So 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 1, 0 with carry 1. So here 1, 1, here 1 plus 1. So 1 plus 1, 0 with carry 1. So there is a overflow here. So overflow is there. Okay. So the result is the minus 75. So the carry out of the sign bit position. So this indicates overflow. Okay. So in that way, we can solve the arithmetic operations. You can perform any addition, subtraction like that. And second one, derive the circuit for a 9's complement when decimal digits are represented in excess 3 code. The mode control input determines whether the digit is complemented or not. What is the advantage of using this code over BCD? So to derive the circuit for 9's complement using excess 3 code representation of the decimal digits with the mode control input, we will first understand how the excess 3 code works and then design the circuit accordingly. So in order to design the circuit, first we should familiar how to get the 9's complementary value, and also know how to get the excess 3 code. Okay, so excess 3 code. So excess 3 code is a binary coded decimal. It is a BCD representation where each decimal digit is represented by adding 3 to the corresponding 4-bit binary number. So see here, we are adding 3 to that number. Suppose if we have a plus 3, we have a 3. So 3, how we can represent? So 0, 0, 1, 1. So this is a binary representation of the 3. So what is the equivalent excess 3 code? If you want to get the excess 3 code, then we have to add 3 to that number. So 3. So we have to add the 3. So 3 means 0, 0, 1, 1. So if you add 1 plus 1, 1, 0, 1 plus 1 plus 1, 1 with carry 1, 1, 0. So this is a excess 3 code. So in this way, by adding 3 to the any digit, we can get the excess 3 code. Okay. So for example, decimal 0. So what is the excess 3 code for 0? So 0 plus 3, that means 3. 3 is the excess 3. Decimal 1. So what is the excess 3 code? 1 plus 3. So we need to add 3 to that number. We have to add 3 to every digit. So 1 plus 3, 4. So we got the 4 value. 2. So 2 plus 3, 5. That means 0, 1, 0, 1. So in this way, we can get the value of excess 3 code for any number. And now let's derive a circuit for 9's complement operation using excess 3 code. So circuit for complementing in excess 3 code. So the circuit, it consists of some input, complement logic, and 9's complement logic, then output. So these are the circuit consists of. So input. So the circuit will have a 4-bit input representing the excess 3 code of the decimal digit 0 to 9. So it is having some input, excess 3 code input. So that will be converted into the 9's complemented value. So additionally, there will be a mode control input. In addition to the input, some other input also there. That input is called mode control input. So mode control input. So that means the circuit what we are going to design, that can be used to perform both addition as well as subtraction. So when it acts as a adder or when it acts as a subtractor, that depends upon the mode control input. So it can be represented with a m. So when m is equal to 0, it acts as adder. When m is equal to 1, it acts as subtractor, BCD subtractor. So that's why that mode control input, it can be, we can call the complementer. So complementer input. And coming to the complement logic. So if complement is equal to complement, or we can also call M mode control input. If complement is equal to 0, it means we won't want to complement the digit. So we simply pass input through. Okay. So that means when m is equal to 0, we are not complementing the given input. We are complementing input only if m is equal to 1. If m is equal to 1, then we are computing the 9's complemented value. See, 9's complement logic. So in the XS3 code, the 9's complement of digit is obtained by subtracting the digit from 9. Okay. So for each bit of the input, we subtract it from 1. So you will need some XOR gates to perform the subtraction for each bit. So using this XOR, we can perform the subtraction by complementing the given input signal. The output of the XOR gates will be the 9's complement of the input digit. And finally, we will have a output. The output of the circuit will be complemented XS3 code representation of the input digit. So this is a one stage of the decimal arithmetic unit. So this is a circuit. We can use the circuit for performing both addition as well as a subtraction. So this is a here. So this is a one input and it is a another input. So between them we are going to perform addition or subtraction. Whether you are performing addition or subtraction, that depends upon this mode control input. So if m is equal to 0, if m is equal to 0, it is acts as a adder. If m is equal to 1, it acts as a subtractor. Okay. So see, so when m is equal to 0, whatever the input applied to the BCD 9's complementer, it doesn't perform any complementer. So directly whatever the input is there, that will be bypassed through it. It can pass through it, and the output. So the outputs are x1, x2, x4, x8, and inputs are b1, b2, b4, b8. So when m is equal to 0, x is equal to b, xi is equal to bi, where I is equal to 1, 2, 4, 8. That means we are not performing any complement. Simply we are throwing the input to the output. Okay. So then this input A1, A2, A4, A8 are added with x1, x2, x4, x8, so that it performs the addition operation and it gives the sum S1, S2, S4, S8 as the result. And CI is it is an input carry from its previous stage. And Ci plus 1 is it is a carry to the next stage. Okay. So just before we have seen how the circuit acts as a adder. Similarly, the same circuit we can also use for the subtractor. So see here. So in order to perform the circuit as a subtractor, the m should be equal to 1. So when m is equal to 1, the circuit acts as a BCD subtractor. So how we are performing? Suppose if we are performing a minus b subtraction. So so this is a value, p is here. Okay. So how we can perform? So this is equivalent to a plus complement of b plus 1. So a minus b is equal to 1's complementing of the B plus 1 to the A. Okay, so by adding these three, it gives the result as equivalent to the A minus B. Okay, so that's why, see here. So B is the value. So it is a given B1, B2, B4, B8. So for this, we are performing nines complement. We are performing nines complement. Then we are adding 1. So the CI is it is an input carry from the previous stage. So if CI is equal to 1, if CI is equal to 1,